Next page, page 3. Now we're going to move on to what's called expected value. And the expected value of an event is the value or outcome that should occur when the experiment is performed many times. And I'm talking about like hundreds or even thousands or hundreds of thousands of times. When we perform an experiment many times, the expected value is what should occur normally or most often. So in our previous example, that would have been 7. A sum of 7 on 2 dice should be our expected value because it's most likely to occur. Example 3. A coin is tossed. If you toss a head, you win $1. So this is a very simple game that we're making up right now. If you toss a tail, you win nothing. It costs you 75 cents to play this game. Now before we get into anything here, does this sound like a very fair game to you? And in your head, if you're thinking, yes, that's fair, or you might be thinking, no, that's not fair. But regardless, we're going to show mathematically why it's fair or not fair compared to the person who's playing the game and the person who's dealing the game. So let's start with, what is the random variable for this distribution? What are we actually measuring here? And it's kind of tricky because it says we're tossing a coin, so you'd think we're looking for heads, but that's not the random variable. It's actually the winnings. It's how much we win. Yes, if you toss a head, something happens, but it's what you win that matters. And winnings is a numerical value. It's either $1 or 0. So let's create a distribution for this situation. X, remember, is winnings. If X is winnings, then what are the two options here? What could we win? Well, we could win $1. We know that could happen, right? Or we could win $0. That's when we win nothing. Winning $0 just means we didn't lose. Losing would be negative. This is winning nothing. What's the probability that I just won $1? Well, I must have flipped a head, so that's a 1 in 2 chance. What's the probability that I won nothing? I must have flipped a tail. That's a 1 in 2 chance as well. So far, we have our distribution table. However, there's more to it than that, because we have one more column to figure out here. And this column is called our XPX column, or what I like to call our weighted average column. The weighted average means what, on average, will we see winning $1 half the time and $0 half the time. So if we win $1 half the time, well then we really only won 50 cents. That's $1 times a half, or X times PX. If we won $0 half the time, well, we still win $0 because 0 times a half is 0. And the sum of that column is actually 50 cents. Now think about why that makes sense. If we're looking for the expected value in this game, are we going to win $1 every game? No. Are we going to lose or win nothing every game? No. We're going to win $1 half the time. We're going to win nothing half the time. So if you think about it, on average, over all of those games that we play, every single time we play, every game has an expected winnings of 50 cents per game. That's the expected value we should hopefully get or win per game. Now, if we get really lucky, sure, we might win $1, 10 games in a row. That would be very lucky, though. We might get very unlucky and win nothing 10 times in a row. But regardless, if we played this over and over and over and over again, it would average out to about 50 cents per game. Now, we haven't actually figured out this now. The second part it said here was it costs you 75 cents to play the game. Well, if we're expecting to win 50 cents per game, but we have to pay the dealer 75 cents every time we play. Well, then in part C, how much would you expect to win per game on average? We're not winning 50 cents every time. We're actually winning. Expected winnings are equal to what we're going to get from the dealer minus what we have to pay to the dealer. So that's actually a loss of 25 cents per game, which is terrible. That's not very fair. If we're going to be losing 25 cents every single time we play, on average, that's not a very fair game. So if I was to ask you if this was fair, definitely not fair. And whose advantage is this for? Is it for the player or for the dealer? And we would say definitely it's in the dealer's advantage because the player is losing money every time they play. Expected value. Example number 4. A committee of 4 is to be selected from 3 teachers and 5 students. If the committee is chosen randomly, what is the expected number of teachers on the committee? Well, now we know what we're looking for. Let's actually figure this out. We'll start with our distribution table chart. Let's think about this. There are 3 teachers to pick from and 5 students to pick from, and we have to make a committee of 4. So how many ways could this go down? X, remember, represents the number of teachers on the committee. Could we have 0 teachers on the committee? Sure. How about 1? Yep. 2? Yep. 3? Yep. Could you have 4 teachers on a committee of 4? No, because there's only 3 teachers. Alright, now we have to find the probability of each of these outcomes happening. What is the probability that we choose no teachers on a committee of 4? You know what that sounds like to me is a probability where we have to choose teachers, and how many teachers and how many students. So out of 3 teachers we have to choose, you guessed it, none of them. Times out of 5 students, well then they must make up all 4 people in the committee. If there's 0 teachers, there must be 4 students. 5 choose 4. And on the bottom, this is NA on the top, by the way. On the bottom, NS is just, I don't care what the restrictions are. There's no restrictions to make up this committee of 4. So 5 plus 3 is 8. Choose 4. 3 choose 1 times 5 choose 4. Oops, 5 choose 3 I meant to say, sorry, over 8 choose 4. I'll stop there. What do you think the next one's going to be? You guessed it. It is 3 choose 2 times 5 choose 2 over 8 choose 4. And the last one is 3 choose 3 times 5 choose 0 all over 8 choose 4. We need to calculate those answers first. We need to know what those answers are before we can go ahead and say what XPX is. So let's do that now. Eight choose 4 is 70. And 5 choose 4 is 5. And we're multiplying that by 0 here because x times px, 0 times our answer. 5 choose 3 times 3 is 30 over 70 times 1. 5 choose 2 times 3 choose 2. Whoops, going too fast. 5 choose 2 times 3 choose 2. Oh, it's also 30 over 70 times 2. Don't forget I'm multiplying x times the answer to this, px, right? For each one, x times px. Last one is 5 choose 0 times 3 choose 3. Well, that's 1 out of 70 times 3. And if we add all of those answers up, we should get our answer here. All right, let's see. We have 30 plus 60 plus 3, all divided by 70. And so the sum, it looks like, is 93 over 70, or about 1.33 teachers per committee of 4. And I'm going to put bracket on average. That's on average because that's not, obviously we can't get 0.33 of a teacher, that's ridiculous. But we can get 1.33 on average. If we do this a million times and we pick committees of 4 a million times, we probably would end up with about 1.33 teachers. Now why does that make sense? Because there are less teachers than students. So if we're making a committee of 4, I wouldn't get 2 and 2 on average. I wouldn't get even amounts. I would have less teachers than students per committee on average.